Okay, so maybe people know that I've been working both in control theory and kinetic equation, and I found this opportunity to to see what we did learn from control theory. And also, it's a follow-up of the talk of Jean-Michel Coron. We did it last week. Now, if you look at what the folklore of control theory for mathematicians interacting with engineers, you find keywords which are feedback, stabilization, observation, and so on. And as Coron has shown to us in this talk, in the nonlinear traditional control theory, these different things are maybe and very often are completely uncorrelated. However, in most linear PDE problems, they follow from what is the observation property, which is much more close to what we do in PDE, and I will focus on that. And I got the introduction in control theory from Lyons, and Lyons, by that time, Senior Lyons, G.L. Lyons, he was working, he was at the CNAM, and he was concerned about stabilizing large structure like satellite antenna, and he observed an obstruction that you see on my slide, which is that people define device to stabilize the first oscillating mode of the structure, but if they do that, they generate oscillation in the higher frequency mode, and they call that overshooting, which was very annoying for the antenna. Now, Lyons studied a model problem, which was just the wave equation, and see how to control and stabilize that. And he found out that in this case, because the system is linear and time reversible, all these options in this case, because linear and reversible, are completely correlated. And so he called that the method. Is for Hilbert, U is for uniqueness, and method was his method. And he gave a sufficient condition in 1987 using an estimate of low phi O, which was published in 1986. And that was enough condition for unconditional stability. Now, it's about the story of the thing. It's interesting to know that this condition was found much earlier, in 1961, by Kathleen Moravec, for a sufficient condition for the exponential decay of the solution of the wave equation, the local decay, in the exterior of an obstacle. So the formula, the mathematics was already done for this thing in 1961. And they got a sufficient condition, which I may come back on. Okay, now by that time, Lax and Phillips and Moravec, they were looking at the decay of the solution in the exterior of an obstacle. And they found out that this is closely related to the propagation along ray of geometric optics. And in this slide, I just take a picture, maybe it's not easy to read, of the page 156 of the book of Lax and Phillips, which goes back to 1967 or something like that. And what they said was that their intuition about how the local decay will be driven will be the propagation of high frequency. They didn't quote by a time the name microlocal, but that's what they had in mind. So follow the high frequency along the ray of geometric optics. Now the ray, they live in a space, they have a position, a velocity, and the dual of the velocity is in the cotangent space of the problem. So they live in a region like that. For the interior, they reflect, and some ray just come very close to the boundary and finally gets in the boundary, and the thing becomes much more complicated when the obstacle is not convex, because you may have a big variety. And that's the reason why Lax wrote, I think it's more in the style of Lax than Phillips, that it is the relation between local decay and the propagation of ray or trapped ray is really related to this question of asymptotic. And if this question of asymptotic will be solved, then they got the conclusion. Now, when we were working on control theory, what we realized in 1988 was that this problem of observation was completely related, was completely similar to the problem that Lax and Phillips were considering. But in 1988, we had at our disposal two papers, the Michael Taylor in 1976 and Melrose in 1979, where these questions were completely solved. And so we find out that to have the inequality which is above, which says that if you observe in this region, which is a small region, and if all the rays cross this region, then you have the inequality 1, which means what you observe in the small region will bound the energy. In this dynamic, the energy is constant, so it's the integral from 0 to t of the initial energy. That means that if you observe in this small region, you control all what's happened everywhere. Okay, and this got the name of BLR condition or BLR criteria. Okay, so far so good. So that's the what I call the prehistory. Okay, now I move on. Now, back. So the first thing to mention about the observation, you want to control something in a domain omega. Here, omega may be either the bounded domain in Rx or a domain in Rx at the dimension t that multiply RT. And you want to know that you want to observe what's happening in a region that may be very small, which I call sigma. And I look at that for an operator P of u equals 0, let's say in an Hilbert space. For simplicity, take L2 to me, and this linear differential operator has a domain with the norm of the domain, and I make the following hypothesis. I assume that the mapping u that you restrict to sigma is continuous for dp. Say, for instance, that if you look at the solution of going back to Lyon's, you look at the solution of the wave equation with Dirichlet boundary condition, then you can define, for instance, the normal derivative of the solution on the boundaries. So this is the situation. And then there is a theorem which says that if this map is continuous, what I said, from the domain to L2 of sigma, and then if sigma is a set of unicity, which means that if u is 0 on sigma here, then it is 0 everywhere. Then there is a positive increasing continuous function, which goes to S from phi to phi of S, which is in R plus T, such that one has the estimate tree, which means you measure the solution everywhere by a function phi of hs over L2 that multiply what you observe. I don't specify this function. I just say that it's increasing and it will depend from u as a function from L2 to hs. As you will see in the proof in the next slide, it's very easy, it's natural. It was not known in the control theory. So I said that it was the Bardos theorem, but in fact, it appears already in a paper in a similar form in an older remark of a former student of Peter Lachs, whose name was Omer Walker. Okay, so, and then it appears also in Melrose in a paper of Tataru somewhere. So, the proof, if you want to do it, it's just by contradiction. You will see it's really few lines. You by contradiction, if this is false, you can construct solution for which this quantity goes to infinity, and all the rest on the right-hand side is bounded. So it's natural to introduce Vn, which is un over Ln squared, and then with this Vn in L2 equal 1, the norm, the ratio of Hs over L2 less than a constant, and the norm of Vn of, and then since I had the hypothesis, this one will go to 0, the norm of Vn in L2 of sigma. Okay, then one more line. Since Vn is in of norm 1 in L2, it converges weakly. But since the ratio between the Hs, the norm Hs and the norm L2 is less than C, it converges strongly. But on the other hand, I use the fact that I have the continuity from the domain of the operator into the observation set sigma. So that means that I have the last inequality, which means at the end of the day, since sigma is a set of uniqueness, and that this goes to 0, that will say that Vn, the limit of Vn is equal to 0, and that's the contradiction. So it's a very simple theorem. Okay. So this type of point, so you have two things, you have the function phi, psi, and you have the u on a small set. Now, in most recent contribution, I will come back to that, it's called propagation of smallness. The second point is that it's called a conditional observation, because to have it, you must have already the knowledge that the solution is more or less regular. In fact, this function psi is a function of the frequency. So that means there are global frequency hypothesis. Now there is even a more naive thing, which is that if the domain dp is contained in the space of continuous function, and then the set where 0 is closed. Then if you can prove that in a small neighborhood, you can extend the uniqueness from the closure of sigma into a small neighborhood, and if the domain is connects, then it goes to 0 everywhere. So then that gives all that gives a kind of roadmap for the conditional stability. For first thing, for a domain of observation, one can prove that if it is 0 there, it's also 0 in a small neighborhood. And then most serious thing is to evaluate, depending on the problem, this function psi of s. And if psi is a constant, you have the unconditional observation. You know that what's happened inside is not big if it is not big where you observe it. Now, many of these questions are subtle. First, the problem of unicity goes back to Kalman in 1939, and he constructs example where the solution is non-zero somewhere, is zero somewhere, and non-zero in another part. And this was a field which really developed a lot. I put two other important steps. An example of place for you don't have uniqueness in an elliptic system. It's not a scalar equation, it's an elliptic system. For scalar equation, there is the other tool that I will mention later. And this is in 1960. And concerning to the problem we tackled with Alignac, with Lebeau and Roche, you look at this wave equation and you add a small term, b of x of t u. You assume that b is infinite and that, but also it genuinely depends on time. Well, that's what we call and in this case, one can it's in two-space variable, one can construct a solution which is zero for x1 negative and which is not zero for xt positive. So that's, I will come back to the example after that. That's an example which will check that I have a comment on that later on. Yeah. So, okay, I will comment on this example later on. So I go back, I go further on. The first example on this story goes back to Hadamard in the beginning of the last century, and you had the Hadamard three-circle problem. You take three circles, one of radius R0, one of radius R, and one of radius capital R. And you look at the solution of the Laplacian of u equals 0 in this tree, in the domain, in the region modulus of x less than capital R. Then the theorem of Hadamard is that if you take the sub on the region of size modulus of x less than small r, which is the intermediate circle, then you bound it by a very simple interpolation inequality. It's the sub for x less than r0 at the power r0 over capital R minus that multiply the sub of x over the region modulus of x greater less than capital R that multiply the conjugate exponent 1 minus r0 over capital R. And this is an example where you have everything. You have the propagation of uniqueness, the propagation of the smallness, because this will say that this is small when this first term is small, if the second term is small also. And this idea is really deep, it's really deep. It can be generalized by many people and in very general geometry. And maybe the most recent thing that one could look at, because it's a good series of papers, are the paper of Logunov and Malinikova, and I put the reference in the archives. And they put it in exactly the same thing, except that you don't need circle, you need very few hypotheses on these two sets, capital E and capital K, and they prove uniqueness and smallness, not only when the set A is an open set, but whenever it is an set of Hausdorff measure almost less than d minus 1. D minus 1, let's say the surface in a domain, which is less than the, so it's which is just less than what you have with usual trace theorem in PD. And there are very interesting applications. There are many recent papers on the question of where the eigenvector of the Laplacian will be 0, because as you see, of course, if you have the eigenvector of the Laplacian be equal to 0, that would give point where the solution of the corresponding wave equation is 0. Now, I just have a remark to connect once more with what we did with Jeff, and it goes to the idea of the proof in a nutshell, one part of the proof of the BLR. You start from the wave equation, you have the energy, which I wrote the usual equation, and using Melrose, Sostrand, and some clever trick added by Gilles Lebeau, we find that the energy can be bounded in the observation set, but since it's a propagation of regularity, not a propagation just of smallness, there is a reminder. And the reminder is it's on all the domain, but it's of order less, it's compact with respect to the first term. And then by a compactness argument, you reduce it to the Laplace equation, and you prove that this you can get rid of this term. And this what connects with the example of Bawendy Gulawik of Alignac-Bawendy, and it connects because this example, maybe you don't have it anymore in your mind. It's this equation with a b of x and t, and the b is infinite, and being infinite, and it's enough to spoil the last term, which is here. Okay, but that's a good thing to make the connection with the propagation of the Laplacian. When independent of time, everything works. If you extend to an operator with dependent of time, it may not work. And I forgot to say that, of course, if everything is analytic, we know that function with analytic support, if they are 0 somewhere, and a set which is larger than their 0 everywhere. So, of course, the example of Alignac-Bawendy needs not to be analytic. And same remark for the old example of Bliss. Now, if you look at the proof of the BLR is based on the propagation of something. I will tell you what is the propagation along rays, which are solution of the most simplest dynamic equation. They propagate with their own velocity df of x plus 3 grad x f equals 0, and they leave, then they conserve the energy, they live on the set of c, t, so stuff c square equals t square equal 1 in the domain. And then there are some problem when they meet the boundary. When they meet the boundary, that's the place where you have to change the picture and you have to introduce the generalized broken bicharacteristic flow, which was the thing introduced, I think, by Melrose and Taylor. Okay, of course, and then that's end up with the first connection with a kinetic equation, dt of f plus c grad x f equals 0. So that's the most naive kinetic equation. It becomes complicated. If I go back here, it's complicated let's say here, it's okay up to here, and it becomes more complicated when you meet the boundary, and that's the reason why you introduce another notion which they call the compressed bicharacteristic flow. And compressed, as you see, is because the ray near the boundary are compressed by the boundary at the end of the day. Okay. Now, so this is the most naive equation. Then what propagate? In we have to propagate a mathematical definition of the regularity, because with compactness, it is the regularity which is propagated, and you define, for instance, a micro-local version or near the ray of the frequency ratio, which is the ratio between the H1 norm and the L2 norm, and you show that you can find this quantity which propagate. Then, of course, this propagation of micro-local regularity found out many other avatars with, let's say, work of Burke, Patrick Gérard, and many other people. You can use also Wigner transform. So you can find many different variants of this property between the connection of the observation and its relation. So far, so good. But that's the first simplest example of the equation. Now, if you can move on, and you said that instead of looking at the propagation of micro-local regularity, you can simply look at the propagation of the energy or the density even along the ray. And I will just to discuss that, consider the most simplest example of the kinetic theory. You have dt of u plus v grad xu, that's familiar to anyone, and you have the relaxation term, and I take as a relaxation term something that will relax to the simplest Maxwellian for this problem, which is 1 over the modulus of the unit ball. I take the V in the unit ball, the average over the unit ball. So this is a very nice equation. Now, if A is constant, it's not a big news for this community that the solution will converge exponentially fast to its average, which to the global average, which is computed when you integrate all that, not only with the omega prime, but also with the x. And in this case, there is no spectral gap. Convergence is perfect. Now you put an A of x, and you consider the problem with reflection on the boundary. And it's one line to apply to this problem the machinery that we had in our problem for the wave, and you prove that if you have the geometric condition of the Bardos BLR, which means that all the ray will meet the support of A of x, then, and it's what I wrote here, assume that you have a time t that it's the projection of 0t cross omega, the projection of the broken Hamiltonian flow, here the broken array which reflect on the boundary. Then if this meets the region where A of x is strictly greater than 0 cross 0t, because you need that on a finite time, then for the solution for total mean average, they will satisfy the observation estimate, which is this u of x u0 is less than 3 times u of x. What you observe at 0 is bounded by what the total energy and density. The total energy is bounded what you see on the observation region, which is A of x greater than delta, and the time 0t. That's a very oversimplified version of what other people did. Other people did, I think I quote Antoine, that Lyoto, and they have a big paper where they look at the transition to equilibrium in 2015, and also Clément gave a talk a few weeks ago at the IHES, and there are also some related problem with, I mean, here I have very naive spectral gap. In the Clément talk, the spectral gap was relaxed. Now the question is, what would happen if you relax this condition that all the rays meet the region where you observe? And that's the point I want to elaborate on. In fact, it's a theorem that we try to do, or we did, with Kim Dang Phung, published in a class recently. And the idea is as follows. You look at the same equation. There's a typo here, of course. No, there's no typo. Then, as I said, the estimate is an observation estimate. So I want to look at the corresponding observation estimate, which means I look at the same equation, but I want an estimate that would involve what is observed in a sub-region. The sub-region is not all the space. So I look at the solution, I look at the ray with, let's say, in a bounded domain. I take as a boundary condition the fact that there are no particle which comes in, which means that on the boundary, U is 0 whenever the scalar product with the normal, the incoming normal is negative. I take an initial data, I look at rather smooth solution, and look at, and I introduce also the solution of the heat equation to avoid traditional problem in this field, which I call initial layer or boundary layer. I will assume that the solution of the naive baby transport equation is independent of the velocity at the time 0, so you don't have the dependence. And then I assume that sigma is an observation set, and a set which doesn't satisfy the BLR, but it's an open set for the time being, and T is strictly positive. And then I assume I will introduce a parameter epsilon, which has to be small enough, and I introduce a frequency. Now, if I to compare with L2, the natural frequency will be the ratio between the L2 norm and the H-1 norm. And you see that if the frequency is not bounded, this quantity goes to infinity. So this is an hypothesis on the frequency of the phenomena. Then the story is that one has an estimate. And this estimate is that the norm of the initial data is less than something which involves the time, no problem, which involves the frequency, and also it involves the epsilon, because of course that won't be true for any epsilon. It involves the epsilon, and with a certain power beta, and then with here is what you observe, and you just have to observe at the time capital T to assume that the solution is small. Okay, so that's now I start to work on this problem, and I suggest Fun to help me because I thought that this would help us to understand the propagation of uniqueness for, let's say, the heat equation, which is the next slide. And it's not what happened on the other hand. On the other hand, what turned out, that's really more the property of the heat equation which force this type of theorem. And that's what I want to illustrate in the different step of the proof. Okay, and I say the proof will be done in 4 steps. First, I want to do a very useful but very classical convexity estimate. With this convexity estimate, I can say some word about the error estimate between the solution of the diffusion equation, which doesn't depend on V, and the average of the solution of the neutral transport equation, which when it's average, it doesn't depend also on X. Then after that, this reduce the problem to the observation estimate for the diffusion equation itself. Okay, so move on to there's a first very simple estimate which will give some, which is the following. You look at any evolution equation with an operator du over dt plus a of u, where a is like the Laplacian say, a self-adjoint positive and symmetric operator. Then you look at the quantity d over dt of a of u over u squared, and you compute. And you find out that this quantity is equal to minus dau squared minus a squared u squared over u squared. And this is negative, which means that this quantity, because it's negative, because this is a of u squared, is the norm of u squared, minus u squared minus a of u, because this is a of u squared, but the norm, well, it's wrong when I wrote it. Okay, anyway, this one is the typo here, but that will make that this quantity will decrease with the time. Now, you just integrate this is just, you integrate this quantity, and then you get a log convexity relation, which is that if you integrate from 0 to t, which is that the integral of u0 squared equal of u of t at any time t, that multiply the integral from 0 to t of a of u over u squared. And since the a of u over u squared is decreasing, you can bound that by t time a of u over u squared at the time 0, where exactly appears the frequency function. So it's what people call a log convexity relation, because you take to get a of u squared, here you multiply by u, divide by 1 over u squared, and you get the derivative of the log norm of the log of u squared. Okay, so far so good. Then the next step is to look at the difference between the norm of u epsilon and between the average of u epsilon and the solution u. The trick we use here is a variant of what is well known in kinetic equation, which will be a moment method, which means we don't introduce what was traditional for a while, an expansion of u epsilon, but you look at the average of u epsilon itself. So you average the kinetic equation and you look at what's happened. And if you do that, you end up, you just use what you do, you just take the equation for the first moment of u epsilon and the first moment, second moment, the average of vu epsilon, and you add and subtract this quantity in the equation, and due to the relaxation term, which is, let's say if I go back to the equation, this relaxation term, you add and subtract the influence of this relaxation term. To add and subtract this, you get that it's add and subtract here. So this term, this what will come from the kinetic equation, but then you put this one in, so that it appears here because it will appear here. And then with this equation, you will get that the right-hand side here, that the right-hand side of this quantity, there's a second typo here. There is a V tensor V, which appears here. But anyway, you reduce to the remainder of what is satisfied by the average of V epsilon to this estimate. And since it has two derivatives, it involves, and now you make the observation that the average of U epsilon is the same, at time zero, it's U average zero, and you observe that this term, epsilon x epsilon, due to the standard estimate for the relaxation of the transport equation, is bounded in h minus L2 of RT, h minus 2 that comes from this term, and h minus 1 of h0 minus 1 that's come from the derivative with respect to time and the gradient of x. Then you localize near the boundary, and if you localize near the boundary, you localize inside the domain sigma where you observe, and you obtain that this difference C of U at t minus the average of U epsilon of t at the norm h minus 1 plus the average on zero t L2 of omega 0 t is bounded by a quantity which is bounded in zero, which is bounded by the value of the dynamic of the time zero with a factor square root epsilon 1 plus 1 over the square root of t. Why the 1 over the square root of t? Because you use, as you can, the regularized effect of the diffusion equation to control the loss, the gain of regularity when you go from 0 to t positive for this equation, and also to control the boundary effect. Okay, so this will give you a difference between the average of U epsilon and the solution of the diffusion equation. So modulus of square root of epsilon, you read, since you control the remainder, you reduce the difference between what is known for the classical heat equation and what is known for what you want to know for our kinetic equation. So really keep in mind that this is a term going to zero, which will force the average of U epsilon to go to the solution of the heat equation and satisfy the same type of estimate. So that means that the thing will be reduced to an estimate for the solution of the heat equation. Okay, so for the heat equation, it has a long story. It was also first studied by people attack the problem of observation for the heat equation, let's say, first by global estimate, more or less in the spirit of Lo-Fa-O, with the beginning of my talk. Then they refined it. They use Kalman estimate to propagate from a domain to the domain of uniqueness to a bigger domain to all the domain. And then they have to evaluate the frequency. There are many people who have there are huge number of contributions of that. Maybe the cornerstone will be a paper after the paper, the first paper with multiplier will be a paper of Robbiano, then Lebeau, Robbiano, Tataru, you have many things. And I was just to say a few words to conclude on what we attack the problem with Kim Dang Phung. And the idea to do the problem, you start first from the theorem I want to prove is that I want to use is that what there are thousands of typos in that, is that the solution at time 0, here is t equals 0, is bounded by an exponential factor which will depend on the frequency, what you observe at the time t, multiplied by what you observe at the power alpha. Well, and here there is an omega. This formula is really bad. You have the same omega here, the same omega here. You have alpha, you get 1 minus alpha. And I said, then there is to make reasonable proof on this problem, to make constructive proof, there is a nice step which is due to Gerson and Lebeau. What they prove a formula on the eigenvalue of the Laplacian and the eigenvector of the Laplacian. You consider an expansion on the eigenmode of the Laplacian with Dirichlet or Neumann condition. And you do look at the expansion up to a frequency lambda, which is fixed. And you want to estimate this projection on all the space, on L2 of all omega, in terms of what you observe in a small domain. And this, I take the small domain, for example, here, modulus of x less than r. And you prove that this quantity is bounded by the integral over the small domain of the same thing. Here is the whole domain, the small domain, by the same projection on the by the same function, which is a projection on the first eigenmode. But of course, this diverge, and this diverge with the same type of frequency factor, the square root of lambda over 2 epsilon square. That's the formula of Lebeau, which will be valid not only on a ball, but in any domain. What Phung observed is that such formula can be extended. That you can use this formula in a small domain, and if you inject this formula in a general situation, you just obtain. You can just, for the wave equation, you can have a local estimate for the wave equation, which says the solution everywhere will be bound in a small domain. And then you extend that, you do that in a simple domain where which is charge-shaped, which is a domain where you can use a multiplier. And when you have done that, you play the game of propagation of smallness, and you get it in the general case. Okay, now what I want to conclude on that, which I don't know, get almost to the end of my time. What I wanted to describe in this talk, except the typo at the end, was that the observation notion is something which really goes all across all the equation, from the macroscopic to the kinetic equation and vice versa. In all the first part of the talk, I argue on the fact that if you want to know at the macroscopic level, you better know what happened for kinetic version, namely for the propagation either of singularity or the propagation of singularity, or even the propagation of smallness. And then that was the first part. And with that, also in the paper, already it appears in the paper of Lebeau, BLR paper, is that there is a nice correspondence between propagation of uniqueness, propagation of smoothness, and propagation of uniqueness. Now, with the sixth proof that I sketch, I just the last step, in the last step of my proof, I avoid a tool which is more or less classical, which are Kalman estimates. In fact, it's not completely avoided because it is in the Garrison-Lebeau for estimate, the local Garrison estimate. But on the other hand, I really focus on what's happened when you consider propagation of smallness from a small region where you have the estimate in the small region here, small region, to estimate the bigger region. And this is an idea which is really, it's really natural to put together the estimation of from small to large region. Now, if you go back to the Laplacian and you want to use the convexity of the Laplacian, which are related to the Laplacian, which I illustrate with the Hadamard-Twisser theorem, and then some extension which I wrote, you can just, which maybe I should move up to that. I have time for 1 minute to move that. I should just move 1 second to that. Oops, don't want to waste your time on that. Well, 1 second. Yeah, this estimate, which is really an estimate of propagation related to the Laplacian or any elliptic operator of the second order, then you have a nice interpolation property between what you observe in the domain, what you observe in E, what's happened in any other domain, and in terms of the global norm of the sub. It's simpler for the sub, and it's a type of estimate which is due to Logunov and Malikova. And to end my talk, I can just say that you get a lot of other results when you combine a kind of local estimate for the Laplacian with the global estimate, with the propagation of smallness from the local to the global. And this is a thing where there's a recent paper of Burke-Moyano that you find on the archive that could be used. Okay, that's it.
Thank you, Claude.
Thank you.
Okay, so we have a bit of time for questions actually, even if we started with a few minutes delay. So please, those who want to ask questions, yeah, put your camera and then open your mic, but don't forget to put your camera so that Claude can see you.
Okay, I want to what to do to move to.
So
okay, here I am. Voila. Okay, very good.
What did you do, Claude? I don't see your slides anymore.
Here I am.
Okay, meanwhile, yeah, maybe you should start resharing your slides, Claude.
Okay.
There's a question. Maybe there's a question. Okay. You should redo the share, Claude. I have a couple of questions if there's no. Claude, il faut que tu rappuies sur le bouton vert en bas, Share Screen.
Share screen. OK.
C'est ce que tu faisais.
Partager. Yep, voilà.
Il faut que tu remettes. Voilà, il faut que tu remettes les slides.
Je remets les slides. OK. Oups, je vais remettre les slides. Il faut que je trouve les slides. Toc. Voilà. Les voilà, mais je ne suis pas en...
Ça va, t'inquiète pas, c'est parfait. Alors, une petite question, Claude, juste pour démarrer. L'estimation sur la chaleur de...
Oui.
Alors, je ne sais plus comment tu l'as appelé, cette espèce d'estimation où tu détermines la norme L2 sur tout oméga à partir de sigma avec une...
Clément.
In English, Clément.
Right.
Okay, no problem. Not the word broken English. Okay.
I was in French. Sorry for that. Yeah. So your core estimate on the heat equation that you use later on with Phung.
Yeah.
So the you control the function in L2 on the whole omega in terms of the function on smaller sigma, and the constant depends on a ratio of a regular norm over less regular norm on omega. So you presented initially in the beginning of the talk, you presented an argument by contradiction to prove it. But that's what you do with Phung is an explicit argument based on the heat kernel, right?
Can you speak more slowly? Not French is louder and slowly. As you know, I have a hearing problem. Go back.
So the question is the estimate to control U in omega from U in sigma for the heat equation, is it always constructive? Is it always quantitative? Because the argument you showed in the beginning was by contradiction. And later with Phung, I think you do something quantitative based on the heat kernel.
No, at the beginning, it's something which is okay. Here is the argument. Okay. Then, is that you had in mind?
Yeah.
Then what's the question then?
So is this argument quantitative? Is it constructive?
It's not constructive. I just said that it's a roadmap to look at this type of problem. Just to say that you have a property of what you need. Really, you need all this type of problem to, what you want to know is that if there is something going on in your domain. So the first thing you have to say, if there is something going on anywhere, it will give a signal on the small domain sigma. Okay? And that's just the unique propagation of uniqueness from problem on PDE. And the second thing, I would like to know the size of the left-hand side. And I say the size of the left-hand side depends on a frequency function, which is the ratio when it is, in this example, over L2. It's any compactness, as you have seen in this very naive proof, compactnessing. Now, I just insist on this theorem because it happens in this, it gives a roadmap to look at the thing, and it's very, it's a thing which appears in many other problems. For instance, when you want to find out the conductivity of media just by observing how it reacts to an impulsion on the boundary, then you have a theorem which is due to Calderon, which says that we have a uniqueness in terms of the Dirichlet-Neumann problem, and that's a very good theorem, but it doesn't say anything on on how you would have the amplitude if you don't know the frequency on the inside. And there were later paper of Alexandri, Ullmann, where they inject in the Calderon result an estimate a function psi, and there they can compute the function psi. And it's a problem very different. It's a problem of defining not a solution, but the property of the material, which is slightly most different than what I talk about here.
And can you always make these arguments constructive, quantitative? Can you always
I don't know. I know that paper where people, this is, let's say, even if you look at the original proof or the proof of Ormander for unique continuation, it's not a proof by convexity like Hadamard, where he got the function, but he construct a weight function, exponential tau phi, which will give you exactly an estimate of this type. And what Ormander does in this first book, I should have quoted that much before, which was a book in 1968, and even in the chapter 8, by the way, he looks at linear operator, and he looks at what will be the most natural hypothesis on linear operator so that you would have an inequality of this type, and he called that Kalman estimate. I think which is a generalization of the Kalman estimate and the generalization of the Hadamard three-circle estimate.
Okay. Is there any other question? You could always also ask in the chat. Okay, apparently my mic is not very strong. Okay. Okay, if there's no other question, thanks, Claude, and we'll do a 15 minutes small break. So the next talk starts at, hang on, the next talk starts at 11:20 by Eric Carlin. So see you all in 15 minutes. Thank you. Thank you, Claude.